All right, section 3.2 is called addition and subtraction of whole numbers. If you are trying to sort of look and see how closely this resembles the last textbook or whatever, this is one of those sections that's changed a lot since our last textbook. So those of you who have been taking a look at some of those things, you'll see a difference. Start with, we're going to take a look at the definition of addition of whole numbers. So if we have two disjoint sets, A and B, so like from Venn diagram, that means two circles that are completely unattached, okay, disjoint. They're finite. If n of A is little a and n of B is little b, that means that's the cardinality, how many things are in them. Then if you were to add A plus B together, it would be the same thing as finding the number of items in the union. This is because they're disjoint. The numbers little a and little b are called the addends. Have you heard that word before? Addends. And A plus P is called the sum. And I do know that that language is taught currently in schools because it's come home through my children's paperwork at different times. Addends and sum. All right, so the first thing we're going to explore is this issue of why it talks about these sets being disjoint. Okay? So it says, give an example to show why the definition of addition has to have A and B disjoint. All right, so what we're going to do is we're going to actually create one where they're not disjoint and see how that sort of fails. Okay, we're trying to say that this really matters. So what we're going to do is we're going to create sets A and B where they actually have something in common. So tell me what you would like to put inside of set A. Don't go crazy on me. Just put a few things in. 1, 2, 3, 4. Thank you, Kaylee. Alrighty, let's put something inside of set B. 3, 4, 5, 6. And I'm going to put a 7 just because I don't want us to think that there's something special going on because they're the same size or something like that. Okay? All right, so we're going to do some counting. N of A, that is how many items are in set A? What is it? 4. N of B, how many items are in set B? 5. Okay, so what if I take N of A plus N of B? What do I get? That's 9, right? Just 4 plus 5. That's all I'm asking is 4 plus 5 there, okay? Okay, let's go back over here. Basically, I've done this side over here. That should be a lowercase b. Sorry about that. That should not be uppercase. I used a lowercase b there before. All right, so I did the left-hand side. I added the individual size of each of my sets together, okay? I also want to look at the number of items in the union. So let's go back over here and use what we know from set theory that we just finished. What is A union B? I don't want to know how many things are in it. I just want you to tell me the things that are in it right now. What is it? 1. What else? 2, 3, 4, 5, 6, and 7. Remember, union means I get it all. It's the marriage ceremony, right? Yours, mine, and ours. What is the number of items in this union? 7. Why are these different? What happened to create this? Yes. When I counted the sets separately over here and over here, I counted 3 and 4 twice. I don't want the double counting. That creates problems. That's why this definition has this idea of the things needing to be disjoint in order for this definition to work. All right, here's what we're going to do. We're going to do these first 2 models for set addition, and then we're going to stop for this one and take a look at some group work. All right, so a couple models for addition. This first one's called the set model, and it is typically used for whole objects. So imagine that you have something that you can't necessarily, break into pieces, or if you did, it doesn't really make a lot of sense. So crayons is an example of that. That's what this particular one's going to be. But you could talk about coins. You could talk about cupcakes. You could talk about dogs. You can't break the dog apart either. That would be okay. Anything that you don't really break into pieces and really talk about in that way. Not to say that you can't break a crayon or you can't break a cupcake, and hopefully you don't break the dog, but that's not what we really think about when we say cupcake. We think about the whole thing, right? Okay, so you're thinking about something that's a full, whole object. All right, so here's an example of set addition, or a set model for addition. Liz has 3 blue crayons and 2 red crayons. If she combines all the crayons, how many crayons does she have? So what we're going to look at is called a concrete model. We're just going to draw the picture of Liz and her crayons. What was her color first? Blue. She has blue crayons. And so we're going to draw. There's my 3 blue crayons. It looks more blue on my screen, just so you're aware. It really does. And then she has 2 red crayons. Obviously very patriotic. And the question is then, how many total crayons does she have? Well, she has 5 crayons. And this is exactly where you start when you start talking about addition with little kids, is you're actually physically touching objects, right? So if you were doing this, you wouldn't be drawing the picture on the paper at all. You'd be actually picking up crayons and putting them together and counting them when you were done. This is called a set model for addition. It's objects. I'm counting objects. That is slightly different than the other model. The other model is a number line model or a measurement model. Depends on the resource you use. And it's typically used for objects that can be partitioned, broken into pieces. Like that's actually how we do it. So here's an example of an object that we break into pieces. If you're talking about wood, how long the piece of wood is, right? You don't say I've got wood, you've got how much wood. It's always about the length of it. So we've got Joe. Joe has 4 feet of wood and 3 feet of aluminum. How many feet of building materials does Joe have? And so when we think about this one, we are much more likely to think about this in terms of a number line or putting his objects sort of end to end. He is supposed to have, 4 feet of wood. So here's where 1 foot would fall. And then we've got our 2nd foot. Our 3rd foot, it did start out at 0, I guess I could label that. And then he has his 4th foot of wood. And we could actually physically put this end to end, and we're not counting the logs, right? We're counting the length of the logs, which is slightly different. And then he's got his 3 feet of aluminum. So you've got 1, 2, and here's my 3rd one. So we have, and if we're counting over, this is sort of like we've counted over to 4, and we've counted 3 more over, and the question is, where do we end this discussion? Well, 5, 6, 7. The answer is 7, so he has 7 feet of material. You're not counting the objects, you're counting the length of the objects. Now, you're probably looking at it and saying, well, that doesn't really look a lot different. But what happens if you notice that the kid can always count objects, but they can't ever seem to count length of objects? Does that give you some kind of an idea of where they're struggling? It does. It helps you to understand that the problem's not knowing how to add. The problem is this specific type of addition that they're struggling with. And that gives you more insight into how to help them. Okay? All right, we'll pick this up next time.